Good morning. I hope you are able to see my screen. Nimai?
Yes, sir.
Okay, good. So let us begin. So welcome to this second class on the automata theory course. Now in the last class, we had a general overview of the nature of automata theory, and we also looked at the practical aspects of running this course. We always begin by asking you if you have any questions about the last class. Of course, we didn't do anything very specific there, just give you an impression of what the subject of automata theory was. So any questions? You can unmute yourself and ask. Okay, if there are no questions, then let us begin. Today we will begin with our study of automata theory, and today I'm going to cover a topic called deterministic finite state automata. Okay, we already referred to these today. So first I want to talk broadly about what are called decision problems. And then I want to introduce a standard way of representing these decision problems at what are called finite word languages. So one thing you will learn today is to how to represent problems as languages. Okay, this is one thing that you will learn today. One of the two things that you will learn today. Then we will introduce the model of deterministic finite state automata. And the second thing you will learn is how to model, problems as finite state automata. So these are the two key things that you will learn today. We'll do some examples of finite state automata, and then if time permits, we'll go into what is called the big step semantics. But this is optional. We'll see how we progress. So my aim is not to rush through this, and I encourage you to ask questions. You can just unmute yourselves and ask. Okay, but otherwise keep your microphones muted, please, and also your videos. You should just see the slides. Okay. So let us begin. Now the material that I'm covering today is given in lectures 2 and 3 of Cozen textbook, and it's also given in chapter 1 and 2 of the second textbook, Hopcroft, Monmani, Ullmann. They have more or less same material, but the notation we are following is from Cozen, although Hopcroft gives more explanation. Now, both these chapters contain more than what we are going to do. Okay, especially there are some parts of these chapters which deal with how to write proofs in mathematics, and that we will tackle in future as we need. So we are not doing the proofs, but we are doing the rest of the material. Okay, so decision problems. Well, there are many kinds of problems, calculate the 10th prime number, given, or calculate nth prime number given this value n, etc., etc. And that will produce as an answer a number. But here a decision problem is a definite problem with a definite answer, which is either yes or no. So decision problem is a problem which has yes or no as an answer. Okay, you got it? Now, how do we represent such a problem? So, for example, what is a typical decision problem? You are given a natural number and you are asked whether it is a prime. So is the given natural number n a prime? And n here is the input or the instance of the problem. And we have to determine whether it's prime or not, right? This is the nature of a decision problem. We are going to see very many different problems in a moment. But how can such a problem be formulated? It is formulated as a pair of sets A and B, where A is the set of inputs for every candidate. So for example, in the prime question, every natural number is a candidate. We have to determine for that candidate whether it's prime or not. So first we have to specify what are the set of inputs for our problem. Okay, and that is set A. Now for some of those instances or input, by the way, these inputs are also called candidates or instances. So I will use these three names exchangeably. Okay, so for every decision problem, you have to know first of the candidate space from which solutions are to be drawn, right? Which is A. And then, a subset of those will be answered as yes. That subset is collected in a set called B. So B is the subset of A for which the answer is yes. Now this B is not necessarily known beforehand, otherwise there is no problem to solve. So B is usually given implicitly using some of the properties of the problem. Okay, so B is not something that is computable, but it is given implicitly and mathematically, sometimes even in English. And the decision problem is given a candidate X belonging to this input space A to determine whether X belongs to B or not. So is the abstract nature of formulation of a decision problem clear? You are given A and in some implicit form the subset B of yes instances. So let's see some examples that will make it more clear. Okay. So first example is to decide whether a number is a prime. This is the first bullet I have here. Okay, look at that. So question is a given natural number a prime number? Okay, that is what we want to determine, right? And so how can such a question be formulated? Our set of candidates A is the set of natural numbers. Okay, for this example, let's take natural numbers to be 1, 2, 3, 4 up to infinity, right? And B is the set of all those natural numbers which are primes. Of course, prime is a mathematical definition, and really in order to solve this decision problem, we will have to figure out a step-by-step method by which to determine whether a number is a prime or not, right? And the way we would solve this problem would be, given such a natural number, we would try to use something like the sieve of Eratosthenes. For all numbers up from 2 to n, we will first remove multiples of 2, right? Then we'll remove multiples of 3. We'll go on like this, and if the number remains, then it's a prime. So you know methods to determine how a number is a prime, and we use this. But we formulate the set of yes instances as this set. So any difficulty with this example? Okay. There are no questions. TS, if there is a question in the chat, please read it out. Yeah. Second question is, given a natural number, we want to determine whether it's a power of 2. So our set of candidates is the set of natural numbers. And what are the yes instances? Yes instances are all those natural numbers n such that there exists another natural number I such that n is equal to 2 to the power I. That is, my number n can be written as 2 to the power I. Let me give you a very simple example. Suppose I give you number 8, and I ask whether this is a power of 2. I can write 8 as 2 to the power 3, right? 2 into 2 into 2. And so this will be, for 8, the answer will be yes. Or rather, 8 will belong to this set B. If I give you 9, there is no I such that 9 can be written as 2 to the power I. So 9 will not belong to this set B, right? And you should get familiar with such set builder forms of writing sets. So I'm specifying the set B in this set builder notation, where I talk about all the collection of all n's having some property, and the property is given after this bar. It says collection of all n such that this condition holds. Okay, so I think you remember this set builder notation from your school, and that is what very often it's given. But sometimes we give English description of what property the candidate should satisfy in order to answer yes. So another example is that of Euler graphs. So given a graph, you want to ask whether it's an Eulerian graph or not. Now, what is a graph? So let me give you an example. A graph consists of a set of nodes. So in this case, I've got 4 nodes and a set of edges which can undirected edges which connect the nodes. So there could be something like this, and something like this, And there could even be a self loop like this, right? So this is a graph. This graph has got 4 edges. So if I number these edges as number these nodes as let me do that in black, as 0, 1. I give some names to these edges, 3. So my set of vertices of the graph is 4 vertices, 0, 1, 2, and 3. And what are the edges I have got? Edges, each edge is given as a tuple of vertices. Okay, and my graph consists of a set of edges. So what are the edges I have got here? I've got an edge 0, 1. So I write a tuple 0, 1 and put it in the set of edges. I've got a vertex 0, 3 and I put it in the set of edges, and so on and so forth. I also have a vertex 2, 2. You know, 2 is connected to itself. That can also happen, right? So is the notion of and because the set of vertices is finite, we call this as a finite graph. Even without qualification, we will deal only with finite graphs here, right? So I hope the notion of what is a graph clear to you, right? Now, given such a graph, you know, such a graph is said to be Eulerian if it has an Euler circuit. What is an Euler circuit? An Euler circuit, oh, so this thing is overflowing. Euler circuit starts at a node and it goes around the graph following the edges and it comes back to the same node. And the condition is that in this circuit, you must return back to the original node and every edge must be visited exactly once. So is the condition clear? So I will, for example, draw another graph here. You know, I will draw a graph which is like a triangle with 3 edges. So here I have another graph, right? It's a triangle, maybe even with a loop, you know. So this graph is Eulerian. Why is it Eulerian? Because I can start at an arbitrary node. I can follow this edge first. Then I follow this edge first. Both have been. Then I follow this edge. I never repeat an edge, although vertex is being repeated. And then I come back here. And so I have here a circuit which begins at this node. It ends back at this node. And it traverses each edge exactly once. So exactly once is important. And since such a circuit is possible, yeah, we call it an Eulerian circuit. And existence of Eulerian circuit says that this graph is Eulerian. Okay. So is the notion of Eulerian graph clear? Now, is the graph on the top Eulerian? Some of you can answer in the chat. No. It's not Eulerian. Somebody is saying. No, is there anybody who says it's Eulerian? Okay, so it is not Eulerian. Lock kar diya jaye. Now, you know, it's not sufficient to just guess an answer. That's okay for multiple choice quizzes, but you really have to give us a reason as to why you think this is not Eulerian. So the person who said yes, by the way, say your name. And can you give us some intuition as to why this is not Eulerian?
Because it is not comeback return on the initial point. Suppose we start from a 0. So if we go on first point vertex, so we can't able to come return. Right.
We will sometime have to cover this edge 0, 1, right, in this direction. But then how do we come back to 0? There is no exit. So, you know, this graph is not Eulerian. In fact, you can very easily verify the following condition. By the way, this problem of whether a graph is Eulerian or was given by a famous mathematician Euler. You know, it is also called the Königsberg bridge problem. And you can read about it in Wikipedia if you like. Okay. So what he said was following. If the graph is Eulerian, right, then every vertex of that graph will have an even degree, because you know you will have to enter that vertex and you will have to exit that vertex, right? And if you've got an odd number of edges connected to a vertex, you can, you know, suppose 3, then you can enter once, you can exit once, you can enter again, but then you will never be able to exit, right? So is the reasoning clear? That, you know, in an Eulerian graph, every vertex must have even degree. That is, number of edges, you know, impinging on a vertex has to be even, because you have to be able to exit and also return. And this exits and returns must match. So, you know, for every such pair, exit and return, it will take out two edges, and you know, there may be many edges connected to a vertex. Uh, uh, you know, the number of such edges have to be returned. So what Euler gave was what is called a sufficient condition. So let me add a page. Yeah. So if graph is then it has then every vertex has even degree, right? That is even number of edges connected to it. Okay.
Sir, I have a question.
Yes.
Doesn't this the condition apply to every node except the start and end?
No, the start and the end node are the same. We are looking for a circuit, not for a path. So this condition applies to every node.
Okay, so you have to start and finish at the same node.
Yes, yes.
Okay, got it.
Yeah. There is a more general condition. Given a start and an end node, there is an Eulerian path which starts at the start node, ends at the end node, and every edge must be visited once. But we are talking about circuits, Euler circuits. Okay, good question. Okay, so this is actually a necessary condition. That is, if the graph does not satisfy this, yeah, then it cannot be Eulerian, right? But is it sufficient? Are there graphs which, oh boy, this tablet, no, sufficient? That is, suppose there's a graph where every vertex has even degree, then will it be Eulerian? And in fact, Euler proved that this condition is not only, so this is a statement of the form if then, right? And you have to give a proof of this, and Euler gave a proof. I won't go into the proof, but it says give me every Eulerian graph, then I can prove that every vertex has even degree. And he proves it by contradiction. You know what he does is he says that suppose the graph is Eulerian and there is a vertex with odd degree, then you say consider, so that it will have an Euler circuit. Now what happens to that circuit at that vertex? You know, he argued like that, and he showed that that cannot be. You will get a contradiction. So that vertex you will be able to enter but never come out, right? And that is why this condition is necessary. And he also showed that this condition was sufficient. That is, the converse of this statement also holds. Converse means what? Whatever we give after then becomes the part of it. That is this part. Let me draw it with red, or let me draw it with black. You know, this part which is given in black, if I put it as, you know, what we have said is, this statement is of the form if A then B, right? Converse of this statement is if B then A. That is, converse of this statement is if the graph, every vertex of the graph has even degree, then the graph is Eulerian. Okay, that is the converse condition. And what Euler did was he proved the converse of this statement also. Okay, and that showed that this condition was both necessary and sufficient, right? So in this course, there will be many problems about automata where you will be giving some statement about the automata and you will be proving both necessity and sufficiency of the statement, right? Typically, what will happen is you will be given two sets. You know, so let me add a page. You will be given sets A and B. And what you will be required to prove is set A is exactly equal to set B. And the method of proof is to show that A is a subset of B. That is, for all elements X, X belongs to A. Then X belongs to B, right? This is proof in one direction. This is like the if-then statement we showed there. So this is one thing we show. And the other thing we show is that B is the subset of A. That is for all X. This is the converse. If X belongs to B, then X belongs to A. By the way, this symbol here is pronounced as for all, right? There is a dual symbol which we are not used in this statement. It is written as this, some sort of mirror image. This is inverted A, and that is used for all. This mirror image of E is used for there exists. Okay, so these two symbols we will use a lot. Okay, so in the course, we will very often be required to prove that two sets are equal, and we prove that by showing that A is a subset of B and B is a subset of A. So they have to be equal. And this is like a necessary condition. This is like a sufficient condition, and we prove the two are equal. But, Hofcroft, Motwani, Ullman have a long, I think sections 1.2 to 1.4, which talk about nature of giving such proofs, and Cozen has some algebra on sets which will allow you to give such proofs. We will consider those topics later in the course, not just now. So the idea of this determining whether a graph is Eulerian graph or not is also a decision problem. What is the set A? A is the set of all graphs. I think that part is missing here. So in this problem, A is the set of all graphs and B is the set of Eulerian graphs. And given a candidate, we have to determine whether it belongs to B or not. Okay. Now, automata are mechanical devices which solve decision problems. So given such a decision problem, you want to build an automaton or a computer which for any instance, you can give that instance as input to the computer and it will produce yes or no as an answer. So automata are, problem solvers for decision problems with yes, no answers. So this is the first thing that you should remember. Okay, this part is not showing up in the slide, but I'll correct the slide so you will get the correct version. So what's a decision problem is clear to you, and what is an automaton? Automaton is a mechanical device or a computer which will solve such a decision problem. Now nowadays, of course, we write an algorithm and give it to a Pentium computer and it will solve it. We'll use a compiler in the way, but these formulations are, for every problem you can think of, a dedicated powerful computer which will solve this problem, right? Now, one question that arises is when we build computers to solve decision problem is how is the input given to the automaton? This line. Okay, we cannot give a graph to the computer or we cannot give a natural number to the computer. We have to encode it in some way so that the computer can read that input, right? So is the question clear to you? And the answer is that each input or each instance or each candidate is encoded as a string of symbols. And this string of symbols can, for example, be, can be encoded. Okay, so what are the symbols that we use? We can choose some finite set of symbols that we want to use for encoding our problem. And this finite set of symbols, in which we are going to encode our problem is called the alphabet. And typically alphabet is denoted by this Greek letter capital sigma. So we'll use capital sigma for alphabet. And for every decision problem, we will specify what is the alphabet in which we will encode it. And then the problem, input to the problem will be encoded as a finite sequence of symbols over sigma. Okay. This for example, we can encode the problem as text file where each character is drawn as a Unicode character. So, there is this standard set of alphabets called Unicode, and we can write down it includes Hindi characters and English characters and Greek and everything. Or you can use ASCII, which contains only the English alphabets and some printable characters, symbols like comma, equal to, etc. We can encode our problem in that, right? And given that alphabet, we can store this sequence in a file and give that file to the computer to solve. So we want to serialize our input. That is what we want to do. So it's the notion of how to formulate the problem instance or the input to the problem as a sequence or a string, clear to you? Such a sequence is called a string or a word. These are the words we are going to use. Okay, sorry, I'm running out of word. Okay, and here let me give you some examples if this is not clear. Suppose our alphabet is the set of decimal digits 0 to 9. Any natural number can be given as a sequence of digits. In fact, this is exactly what you type in when you want to type in an input, integer natural number as an to be given to your C program. You will give it as a sequence of digits, and somewhere in C there is a function which will convert this sequence into its equivalent natural number, right? So a natural number can be given as a sequence of decimal digits. That is the natural way in which we use, and very important, there is 0, because of which we are able to give any number as such a sequence. And discovery of 0 was done by Indians, and they discovered this positional numbering system. So ancient India has a lot to do with this method of representing natural numbers. Okay. But there are other ways in which we can give natural numbers. We can encode a number, sorry, spelling mistake, in unary. So suppose we have an alphabet consisting of a single letter. Now what that letter is does not matter. We can call it A, we can call it B, we can call it tick, whatever you like, right? And a number n can be encoded as a string of A's where there are n occurrences of A, right? So is the encoding of number A clear? Basically, we have A repeated n times. And this is the way, if we give this string, the computer will try to understand that this represents number A. This is called the unary encoding of number, right? And this AAA occurring n times is written in short by this symbol. So A to the power n actually denotes n repetitions of letter A. So I hope this notation is also clear to you. Now, to determine whether a number is prime or not, we can give to the computer this number n in unary, or we can give it in decimal. So we have to choose. So for every formulation of the problem, we must decide what is the alphabet and how we are going to encode the problem using that alphabet. Now, one question that arises is, for us, natural numbers are 0, 1, 2, 3, 4, 5. So what is the encoding of number 0 in this unary encoding? It should have 0 occurrences of A, right? 1 will have 1 occurrence of A. 3 will be encoded as AAA, right? 2 will be encoded as AA. But what about 0? 0 will denote some sort of empty string where there are no occurrences of A. You cannot even see it, right? Such a sequence of 0 A's is denoted by a special symbol called epsilon. Okay? So epsilon denotes empty string, empty sequence, a sequence which has no letters in it. Confusing, or it's okay? The need is clear, right? Otherwise, there's no way in which we will be able to represent 0. So this epsilon is a very useful and standard part of encoding problems. Okay. I hope there are no questions. If there are questions, feel free to ask. Next, we will consider yet another way of representing numbers. So we are going to consider 3 ways. One is this decimal encoding, one is this unary encoding, and third is the binary encoding. In binary encoding, the alphabet is 0, 1, right? And we encode a number 9, a number n in its binary form, right? For example, 9 can be encoded as the string 1001. Now, I hope you are all aware of binary encoding of numbers. Is there anybody who has not seen how to represent a number in binary? These are the kind of representations that the computers use, internally. So whenever, it wants to do calculation, it will basically work on the binary representation of the numbers and do calculations on this. And why is this binary representation used? Because, each bit or each digit, which is either 0 or 1, can be represented by a value of a electromechanical or a transistor element, which is either on or off. So, you know, some sort of on-off relays can reliably represent such bits, and calculation can be done very reliably and very fast on it. This idea of using binary system for representing encoding things was proposed by many people, but most prominently by Shannon, you know, who built one of the first computers using electromechanical relays. And you know that rather than using gears with 10 tooth for decimal system, you know, this system turned out to be much more reliable and fast. So binary encoding is at the heart of all the digital electronics and digital processing of information. Does anybody not know this binary encoding? If that is the case, please speak up or answer in the chat that you do not know the binary encoding of numbers. Then I'll spend 2 minutes explaining it. Okay, so you are all familiar with binary encoding of numbers, and we will let that, we'll assume that you all know that. Okay, now, you know, so for every problem that we want to formulate, we will give its alphabet, right? And then we will encode the instance as a string over that alphabet. So let me give you some examples.
Sir, there is a question on the chat.
Yes, what is the question?
Why
Can you
can't?
speak? Yeah.
I'm a TA, sir. So there's a question on the chat. So why can't we just pass elements of the input set A as the inputs rather than serializing them in this way?
How will a computer read? You know, suppose you have got a number 10 billion, you know, how will you pass that 10 billion? Or if it's a graph, it's a picture. Do you want to pass it to the computer as a picture? And if the graph has got a billion vertices, how will you give it? So the only way to give large inputs is by serializing them, right? See, a mechanical device cannot take, you know, a picture with arbitrary precision of, you know, how it, so if it's a billion node graph, you know, you will draw it very, very fine, and you know, even the computer may not be able to read it reliably. So in order to make the input available to computer, you know, basically we give it as a sequence, and the computer will read it as one symbol at a time. This is something which is very easily possible for computer. Nowadays, of course, other methods are being used, but this has become the standard way of giving input to the computer. Okay?
Sure, I thought we are dealing with this more abstractly, like thinking of the computer as a function which takes an input and gives an output.
No, you are absolutely right. You sometimes want to think of a problem more abstractly by directly formulating as sets A and B, as I gave before, right?
Yeah.
But if you want to solve it by computer, you have to encode the problem in a language that the computer understands. And one of the easiest languages that computer understands is a sequence of symbols. Okay. So it has become a standard method in automata theory to code your problems as sequence of symbols, and where the symbols are drawn from a fixed finite alphabet.
Okay, sir, got it.
So we will return to this this issue. I think it's an important issue. And you know, I referred to this very famous, perhaps the most famous computer scientist, Alan Turing, right? In last class.
Yeah.
Now, yes. Alan Turing wrote this one paper which completely changed computer science in 1938, right? Where he defined Turing machines, etc. And there, Turing machines also read a sequence of symbols as input. And he has given a long philosophical argument as to why this is the correct way for an automaton to work. So Turing's paper gives detailed, argument about your question, but it's a philosophical argument.
Okay.
It is possible that tomorrow you may design a computer which will take input as an image with, image processing, right?
Okay.
But given the finite precision with images can be processed, you can only record certain number of pixels from the image using a digital camera, right?
Yes, sir.
So you can always convert this kind of information as a sequence of values read by each pixel. So Turing's idea was that no matter however complicated mechanism you design to read input, it will be equivalent to some sequence of symbols. Because computers don't have infinite precision in recognizing symbols.
Yes, I got it. Makes sense.
Right. So this was his argument, but it's an important question. And Turing thought it was important to lay out the reasons why this was being done. So it's good you are thinking along these lines. Okay. Let's continue. So what we have is this encoding of problems in alphabet, and each problem will be given as a sequence of symbols, finite sequence of symbols from this alphabet. Such sequences are also called words or strings. So I will use words or strings exchangeably. And in specifying these words, first thing is you have an alphabet, which is a finite sequence of symbols. For example, you can have use the binary alphabet 0, 1, and you can encode numbers using this, right? Now in this course, we'll use small letters A, B, and C to range over, symbols or letters. The elements of alphabet are called symbols or letters. In fact, letters is more standard. So we'll use ABC to range over letters, okay? So whenever I use small ABC, they will mean letters of a given alphabet. What is a word? A word is a string over this given alphabet sigma. Then it's a word over this alphabet sigma. It's a finite sequence of letters from sigma. So for example, if your alphabet is binary 0, 1, then a word or a string over this alphabet sigma is something like 1, 0, 0, 1, 0. It's a sequence of 5 symbols. The first one is 1. The next one is 0, then there is 0, then there is 1, and then there is 0. So is the idea of giving, a word over this alphabet clear? This is a word, of length 5. It has got 5 symbols, and in sequence they are 1, 0, 0, 1, 0, right? And we will use small letters X, Y, Z, U, V, W to stand for words. So we will abstractly be talking about some word, and then we will use these letters to range over words. So is the idea of what is a word clear? Word, of course, makes sense only once you fix the alphabet. So it's a word over an alphabet.
So the word can also be empty string, right?
Yes, it can be empty string. In which case, because we cannot write down blank, we will write the symbol epsilon there.
Okay, epsilon. Got it.
Good question. Okay. So epsilon denotes the empty word. That is this bullet. Okay. Yeah. Now, sigma star, given this alphabet sigma, this sigma star is a symbol, and sigma star denotes the set of all words that can be over sigma. Okay. So it's a rather large set. Let me give you an example. So suppose my sigma is AB, 2 letters, A and B. What is sigma star? Sigma star is a set containing firstly epsilon, because that's a word. A is a word, just a sequence with 1 letter. B is a word. Then AA is a word. AB is a word. Then AAA is a word. AAB is a word. Then ABA is a word. ABB is a word. BAA is a word. BAB is a word. BBA is a word, and BBB is a word. I finish all 3 letters, then I go to 4 letters, and this goes on forever. So sigma star is an infinite set, of all the words that you can make out of this alphabet. It's just a notation, right? We will never be giving whole sigma star to the computer explicitly. Okay, we'll be giving elements of sigma star to the computer. But is the notation sigma star clear to you? I hope so. Okay, so sigma star denotes the set of all words over alphabet sigma. Given a word X, this X between these double bars, the modulus of X denotes the length of the word. So for example, if the word is ABAA, then the length of ABA is 4. So I hope this notation is also clear. I'm introducing some basic notation about words to you, which will be useful. So we have to go through a little bit of this kind of understanding before we can begin on the subject matter. So given a word, we can also talk about its length. And the length of a word is denoted by enclosing that word in 2 bars. Okay. So length of ABA is 4. Length of ABA is 3. Epsilon denotes the empty word, and length of empty word is 0. Right? So far simple. Finally, we will come up with a very important operation. Given 2 words X and Y over the same alphabet sigma, we can construct a bigger word by joining y at the end of x. This is denoted as x catenated with y, and this catenation is denoted by putting this small dot between x and y. So x dot y denotes the catenation of x and y. Is the idea clear? So you take the word x, join the word at the end of it, you get a bigger word, and that is called x dot y. Okay, and very often, as in mathematics, when you multiply x with y, x star y, you write it simply as just xy. That star operation is implicit. Even in words, we will very often not write that dot in the middle. So we will see that. So suppose my word x is AB, okay, and my word y is BBA. Then what is x dot y? X dot y I have simply written as xy, omitting that dot in the middle. You know, it will be the word. You first write down the letters of x, which is AB, and then follow it up with the letters of y, BBA. So you get a word which is obtained by catenating y at the end of x. It's a simple concept, right? But important. So is the idea of catenation clear to you? Clearly, you know what is the length of this catenated word x followed by y, x catenated with y? It will be the length of x plus length of y, right? Because all the symbols of x will occur first, and then all the symbols will y will occur. So the total number of symbols letters will be length of x plus length of y. So I hope these things are clear to you. Okay, we'll be making use of these things little bit, but this catenation, you know, just with the concepts that we have defined here, we can now work out some properties of words over some alphabet sigma, right? So first property is that suppose there are 3 words and you catenate them like this. X you first catenate y and z, and that result. So this is given by bracket of x y catenated with z, and you catenate x with that yz. Then the sequence that you get is same as if you catenate x with y and then catenate it with z. So this is some property called associativity of catenation. This is just like associativity of addition, you know, a plus b plus c is equal to a plus b plus c, right? The order in which you do addition doesn't matter. Similarly, multiplication is associative. Catenation of words is also associative. So is this property clear to you? And you can easily see why that is the case. Secondly, we had property of identity. 0 was the identity of addition, right? A plus 0 gave you A. Similarly, epsilon catenated with x will just give you back x. And if x is catenated with epsilon, you will again get x, because epsilon does not add any further symbols. So in some sense, epsilon is the identity of catenation. Mathematicians have studied such structures, you know, which are associative and which have identity. These are called in mathematics as monoids. So natural numbers with plus form a monoid, natural numbers with multiplication form a monoid, and set of words with catenation also form a monoid. Okay, this is just for your knowledge. It's not important to remember for exam that this is a monoid, but these two properties are easy to see. Now, one thing to note is, unlike multiplication or addition, xy catenation is not commutative. That is, xy is not same as yx. You know, for example, you had x was AB and y was BBA, then xy is AB BBA. But what is yx? Can somebody tell me what is yx? What string will it give? Here I've got x and y, and xy we calculated as this string. So what is yx?
BBA
AB.
Right. Now you see these two words are different, right? So xy is not same as yx. So this catenation is not commutative, whereas addition and multiplication were commutative over numbers, right? So this is a monoid which is not a commutative monoid, whereas addition and multiplication are commutative monoids, right? So just for your information. One last symbol, one last notation about words. We'll define the power of a word. That is x to the power n we will define, which means x catenated with itself n times, right? We are trying to define x catenated with itself n time, which is same as x followed by x followed by, you go on like this n times, right? And that can actually be defined recursively or inductively. So you should get very familiar with this form of recursion. First you define it for the base case for n equal to 0. So you say x to the power 0, x repeated 0 times will give you the empty sequence, right? Here, x repeated 0 times, x to the power 0 will give you empty sequence. X repeated n plus time is obtained by first repeating x n times, and you know recursively how to solve this simpler problem, and then through the result you catenate x, right? So basically you will get x repeated n plus 1 times. But this is the kind of primitive recursive definition that we saw yesterday, and most of our definitions will be given in such a recursive form, and you can systematically apply this definition for any n, right? So for example, AAB to, to the power 3, that is AAB repeated 3 times, will give you string AAB, AAB, AAB. We can do a detailed calculation of this using this definition. It will, let me do that so that you get used to, this is how a computer would understand. A computer will understand this definition, x to the power 0 is epsilon, and x to the power n plus 1 is, first you calculate x to the power n somehow, and then you catenate x with that, right? Now, given this definition, yeah, if you ask a computer to calculate, let's say string AAB, right, to the power 3, what will he do? He'll say this is equal to AAB to the power 3. To the power 2, because 3 is 2 plus 1 catenated with AAB, right? In solving this, I have to solve what is AAB to the power 2. So that is same as AAB to the power 1 catenated with AAB. That will give me this string, this part, and then this will be followed by AAB. So computer will expand it like this, and then AAB to the power 1 will actually expand to AAB to the power 0 catenated with AAB. Okay, this catenated with AAB, that will give me this bracket, yeah, and that catenated with AAB will give me the full string. So I can expand this out like this. Now I know that AAB to the power 0 is epsilon, so I can replace epsilon here, yeah, and epsilon catenated with AAB will give me AAB. So what I'll get is AAB catenated with AAB. This was the second bracket, and that catenated with AAB, and this will give me that string AAB, AAB, AAB. So this is the kind of systematic calculation which is implied by such a definition. Okay, so although intuitively for us this is easy to understand, a computer internally will work like this to calculate power. Okay.
Sir, I have a question regarding words.
Yes.
Say I define alphabet sigma. Then it may be possible that every word in sigma star does not represent a valid input in the set A.
Yes. Yes, good question. So, we will encode all such strings as representing a dummy problem, and my decision problem will say out of scope or dummy or something like that. Right?
Okay, fine.
So you are saying that given A star, yes, there are some instances where a string may not encode a problem, right?
Yes.
So usually we should, along with A, also specify which subset of A is valid candidate. Okay, in general.
Okay.
But that's a detail that we will not consider in this course. Although in real problems, A should be specified together with a condition which says which are the valid candidates.
Okay.
So you are right. I mean, this is needed in real life, right?
Okay, sir.
Where are we? We have gone far ahead. We jumped the whole class. Okay. So how are we doing with time? Let us see. Oh, not too much time. So we are not going to be able to do everything, but it's better to go slow than to, is this pace too slow, too fast? We will set up a poll today and you can tell me if the speed is right for you, right? So far we considered words, right? And sigma star was the collection of all words over a given alphabet. This much we learned, right? Now let us go to what is called a language. Language in the sense of automata theory. Huh? So language over a given alphabet sigma is an arbitrary subset of sigma star, right? So every subset of sigma star will represent a language. So there are many languages over alphabet A. These are called artificial languages. There are not naturally English languages, you know, or French language. So artificial language over alphabet sigma is any subset of, you know, alphabet sigma, right? And we'll see many examples. So this concept will become clear to you. You know, we will use capital letters A, B, C to denote languages. And we will typically define artificial languages using set builder notation. You know, set of all strings which are member of my given language. Because you know, which subset of sigma star will I specify? So for example, you know, I want to define you know, prime. So I will give and I will give numbers in unary notation. So I will choose my, oh, this is wrong. This should be capital sigma. My alphabet is the unary alphabet with only one letter. And so a number n will actually be represented as a to the power n. That is a repeated n times. Okay, where a is a symbol. Okay, and my, what is my language of primes in unary notation? It is all strings of the form a to the power p, that is a repeated p times, where p is a prime. So is this way of defining sub? So let me work this out a little bit in detail so that things become clear to you. Okay, so our alphabet sigma is a single letter A. A number n is represented as a string a repeated n times in unary, right? What will be the elements of sigma star? Sigma star will consist of all strings like epsilon, a, and so on, right? All possible strings, you know, by finitely many a's. We want to define a language A where the strings represent prime numbers only. So, you know, 0, of course, we don't consider. 1 is a prime, if you want to include that, you know, so there is debate as to whether 1 is a prime or not. 2 is a prime, 3 is a prime, so 3 a's will be a prime. 4 is not a prime, so you will omit this string from your list. 5 is a prime, so you will put 5. Then 7 is a prime, so you will have 7 a's. And so on, right? This collection A will represent primes in unary notation. And that is this set language A that I have defined, artificial language A of prime numbers in unary. So any questions here? Of course, I have defined this implicitly, you know, by using this ... some sort of set builder notation, right? So this is not an algorithmic way of, you know, checking whether a string is fine. That job is left to automata. Here we are just defining what is this language implicitly. So is the language of prime clear to you? If there is any doubt, ask now.
Sir, you are defining, like you're giving the condition for what the value should be. Like,
yeah, what should be inside A and what should not be inside A. That is all you do.
Yeah,
that defines the language implicitly. Yes.
We are calling it that it is finite set. But
no, the set is not finite. Each word is finite.
Oh, okay.
Sigma star is, so this is, okay, that's a very important point. So a language can be infinite. But each element of the language is finite. Okay. So language can be finite or infinite. You know, there can be finite subsets of sigma star. There can be infinite subsets of sigma star. And for example, because we know that there are infinitely many primes, our set A will be infinite. Right? Is this clear to you? I will give you another
yes, sir.
Another example. You know, Let me go and add one more page.
Sir, battery is low.
So let me
Sir,
have
battery is low.
yes. I can't hear you.
Laptop
Can you
battery-
repeat? So,
Sir,
Can you
laptop
type?
battery is low.
Oh, my laptop battery is low. Yeah, thank you. No, I'll plug in the wire. I have some power connection without earth. And so if I connect the charger, I should not touch the laptop. I can touch the tablet or I get a shock. Sorry. Yeah, it's plugged in now. Thank you. Yeah. Suppose my alphabet is 0, 1. What is my sigma star? What kind of strings will it have? Zero, 1, 1, 0, 1, 1. 0, 0, 0, and it will go on like that. All possible sequences like this, right? This sigma star is an infinite set, right? Now, what are some of the languages I can form out of this over this binary alphabet? You know, one language A could be something like that. It contains 0 and 0, 0. Only 2 words out of this infinite collection. This is a finite language consisting of either 1, 0 or 2, 0. So this is our language. Okay. I could have a language where words are made only out of 0. 1 is never used in those words. So this is a subset of sigma star. So another language is this, etc. Do you agree that this is a subset of sigma star? It is not equal to sigma star because 1 is never used in any of its strings. This is also a language. This is an infinite language, right? There is also a language where we include no string within the language. This is what is called the empty language. This is also a subset of sigma star, right? And finally, we have this language which contains only the word epsilon. This is a non-empty language which has one element, where the element is the empty word. So don't confuse empty language with empty word. These are different things. These are some of the little, technical points that at the beginning of the course you have to pay attention to. But please remember, empty set is different from a set containing the empty word. And some of the languages may contain the empty word, they may not contain the empty word. This language has empty word in it. This language does not have empty word in it. Okay, languages can be finite or infinite, but any arbitrary subset of sigma star forms a language. So here I've got 4 different examples of language A. Any questions?
Sir,
I think you are okay.
sigma star.
What?
Age is not a sub sigma star, so can form a language.
If A is not a subset of sigma star, then it is not a language over sigma. Maybe it's a language over some other alphabet. So when you talk about language over sigma, it will only be subsets of sigma star. Otherwise, it will not be called a language over sigma. This is the definition. Okay. So for example, if you got a language consisting of strings 0, 1, 0 and 1A, this word 1A does not belong to sigma star. So this is not a language over sigma. Okay. So this is just some sort of grammatical check on what are the languages over sigma. Okay. This should be capital sigma. I don't know what happened. I've made this mistake repeatedly. Yeah. Okay. Let sigma be the binary alphabet consisting of symbols 0 and 1. For a word X, in sigma star, the notation count of 0 in X, this count of 0 in X is written like this. What I have overlined, count of 0 in X denotes the count of occurrences of 0 in the string X. Similarly, count of 1 in X denotes the count of 1. So for example, if your string is 10011, then the count of 0 in this string is 2 because 0 occurs 2 times. And the count of 1 in the same string is 3. So is the notion of count of a letter within a string clear? It's an extra notation that we are introducing. Now we define a language A as all words over this binary alphabet in which the count of 0 is same as the count of 1. So what are some typical words which will be there in this language? 0, 1, 0, 1 will be in the language. 1, 1, 0, 0 will be in the language. But 1, 0, 1 will not be in the language. Right? Why? Because the count of ones here is 2 and the count of 0 is 1. And these are not equal. Here there are 2 ones and 2 zeros. So it's fine. Here also there are 2 zeros and 2 ones. So till count of 0 is equal to count of 1, that string will be included in this language. The string can be arbitrarily long. It can be a billion character long, but it should have equal number of zeros and ones. And how will you build a computer which will recognize, strings of this language? Well, somehow have to, as you scan the string of zeros and 1, you will have to keep a counter of how many zeros have appeared so far, how many ones have appeared so far. And then at the end, you can check that these two numbers are same. Or, some people may keep the difference of count between 0 and 1. Every time a 0 occurs, you increment the count. Every time a 1 occurs, you decrement the count. This can be a positive or a negative number. And at the end, it should be 0, right? So there are various computational methods to recognize the words of this language. That is what computers do. But the specification is as simple as this. All those words over alphabet 0, 1, where the number of zeros is same as number of ones. So is this language clear to you? Okay. Finally, here is another language. Again, we have a binary alphabet, and we consider all strings X in binary. These are actually representations of numbers in binary. And we want to include only those binary strings which are represents of numbers of the form 2 raised to I for some natural number I, right? That is those binary strings which will represent powers of 2. Okay, so let me add a page after. And in binary numbers like this will represent 2. 1, 0, 1 will represent 5. You know all how binary numbers represent decimal numbers. What we want to do is we want in a collection of all numbers which will represent powers of 2, right? So A equal to powers of 2 in binary, right? This is what we are trying to. So what kind of strings will be there?
So it will consist only 1 and rest will be all
2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, but in binary. So what is 2 raised to 0? It is 1, and that is represented in binary as string 1. 2 raised to 1 is number 2, and that is represented in binary as 1, 0, right? 2 raised to 2 is 4, and that is represented in binary as 1, 0, 0. 2 raised to 3 is 8, and that's represented as 1, 0, 0, right? So that is exactly what somebody answered. It will have strings like 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, etc. And it will go on like this. So out of all words over 0 and 1, it will contain words like this. It's very easy to analyze this. If in the string, the beginning character is 1, and after that all the characters are 0, then it's a power of 2. Agreed? So this is power of 2 language in binary. So here we have taken some examples of binary, some artificial languages which represent some natural problems, right? Whether something is prime, whether number of occurrences of zeros is same as 1 or not. And okay, here are sometimes we don't use this set builder notation, but we just give it informally. So for example, here is a language which is defined as set of all words over English letters A to Z, which are palindrome. What is a palindrome? Palindrome is a word which reads same whether you read it in the front or back. So if you take a word like noon, if you read it in front, it reads noon. If you read it backwards, then it's N-O-O-N, it's the same word. So a word which looks same whether you read it forward or backward is called a palindrome. And all English letter words without any blanks or punctuations, these are called palindrome words. Palindromes are sentences which read same forward and backward, but here we are talking about palindrome words. And some palindrome words are noon and madam. Now you collect all possible sequences of these letters A to Z, which read same forward and backward, and that will give us a language, and that language is described informally in English like this. So this is the language of palindromes. caution, it will not contain just valid English words. It may also contain something like ABA, right? This reads back. This is not a natural English word. So it's all set of palindromes drawn from this sequence, right? Similarly, another language which is very important to us, this is an artificial thing, but a language, all sequences of ASCII characters, that is all sequences of characters you type from the keyboard, which form syntactically correct C programs, is the language of valid C programs. We don't care what they do, but for example, a program like this, A plus B multiply, this is not a valid C program. It is not even a valid C expression. And this string, which is made out of letters A plus B multiply, is not a valid C program. Whereas, all the programs which are accepted by your compiler, will be valid C programs. So this language of valid C programs is very important for compiler to understand what to execute, right? So that is why these are artificial languages. And one of the key uses of automata is to define languages, artificial languages, which can be processed by computers. Okay, so all the artificial languages like language of C program, the language of Java programs, etc., are very important to us. Okay, again, everywhere I have written small sigma. We will also use this notation for defining languages. Here, my alphabet is a binary alphabet, symbols 0 and 1, and I say A is the collection of all strings of the form A to the power n catenated with 0 to the power n catenated with 1 to the power n, right? Where n is a natural number greater than equal to 0. So what are some of the strings which will belong to this set? 0 to the power 0, 1 to the power 0. What is 0 to the power 0? 0 repeated 0 times, it will give me epsilon. Epsilon catenated with epsilon will give me epsilon. So actually 0 to the power 0 denotes the word epsilon. The next word in this language is 1 to the power 1 followed by, 0 to the power 1 followed by 1 to the power 1. That is 0 repeated 1 time and 1 repeated 1 time. So what word will that be? 0, 1, right? Next word is 0 to the power 2 catenated with 1 to the power 2. For all possible n's, I include words of the form 0 to the power n catenated with 1 to the power. So 0 to the power 2 catenated with 1 to the power 2 will be included, and that will give you me 0, 0, 1, 1, right? So is this clear to you how I form the letters of this language? So this language, in short, will consist of words like this. You should be able to solve, examples of languages like this. So one of the first skills you will learn in automata theory is how to implicitly, specify languages using notations that we have given in these examples. And you will do lots of exercises of this. So this language A will consist of words like this, epsilon, because that is 0 to the power 0, 1 to the power 0. Then it will consist of 0, 1, then it will consist of 0, 0, 1, 1. Consists of 0, 0, 0, 1, 1, 1, etc. And why is this? This is actually, I will write it in blue. This actually is obtained by taking 0 to the power 0 followed by 1 to the power 0. This one is obtained by taking 0 to the power 1 followed by 1 to the power 1. This is obtained by taking 0 to the power 2 followed by 1, catenating it with the 1 to the power. Yes? Hello? Sorry, any question? I am not able to hear it. Can a TA repeat this? I think there was a question. I am not able to hear your question, so perhaps we can do it in doubt clearing. Okay, so this is how we specify the language. Okay, today I think we will just do how to specify languages, and we will do automata in the next class. Okay. Okay, given simple languages, we can construct larger languages out of simple languages. Okay, and there are some standard operations that you can do on languages, and they are going to turn out to be very important. Are you able to hear me?
Yes, sir.
Okay, yeah, because there was a question and okay, we can take that offline. So suppose you are given two languages over an alphabet sigma. Okay, what we can define a larger language, a different language made out of these two languages A and B. So for example, we can take union of A and B because A and B are sets. We can take their unions. So A union B is collection of all words over sigma such that the word either belongs to A or this should be B. So I have made a mistake. This should be B, and similarly here this should be B. I'm sorry, I'll correct this slide. Right? So A union B gives you members of either A or B, put together in a single set. And A intersection B gives you those strings which occur both in A and B. And so by taking union or intersection, given some sets, we can define new sets. A simple example. A is the language of all words of the form 0 to the power I, 1 to the power j, where there is no relation between I and j. So both I and j are greater than equal to 0. Okay. And B is the language X such that the count of 0 in X is equal to the count of 1 in X, right? So you should now be able to understand these two languages. What are some typical elements of A? Can somebody tell me? First, we can instantiate I and j whichever we want till they are a pair of natural numbers, and we can form a string like this, and that will be our language. Suppose we check both I and j to be 0. So you get 0 to the power 0 followed by 1 to the power 0. That is epsilon followed by epsilon. So epsilon will be in this language. What else will be there? We can take I to be 3 and j to be 2. So we'll get string of the form 0, 0, 0 followed by 1, 1. We can also have 0, 0, 0 and no ones because we can take I to be 3 and j to be 0, right? Or we can take 0 followed by 1, 1. But we cannot, what does not belong to this language is string of the form 1, 0 or 0, 1, 0. That is, no 0 can follow a 1, right? Because we are saying we have a sequence of zeros followed by a sequence of ones. Right, that is language A. What is language B? All those strings where number of A's is same as number of B's. Now what will be the set A intersection B? So here is the question. Will epsilon be in my language? Epsilon is in A and epsilon is also in B. Why is it in A? Because we can choose ij to be 0 and then we will get epsilon. Why is it in B? Because number of zeros in empty string is 0. Number of ones in empty string is 0. These two are equal. So epsilon is in my intersection because it's in both A and B. What about string 0, 0, 1, 1? Well, it's a string where there is a sequence of zeros followed by sequence of ones. Okay, so it is in A. Also, number of zeros is same as number of ones. So it is also in B. So it is both in A and B, and that's why it's in the intersection of A and B, right? What about 1, 0? 1, 0 is not in A. It is in B because number of ones is equal to number of B's. So it is not in the intersection because it is not in there. So this I can't include, Okay. What about 0, 0, 1? Let me write it here. 0, 0, 1. Okay, 0, 0, 1 is sequence of zeros followed by sequence of 1. So it is in A, but it is not in B because number of zeros is not same as. So this also I cannot include. So you can see what kind of strings I'm going to have. I'm going to have string 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 1, etc. And I have defined this language using the intersection. Okay. You can also define complement of a language. What is complement of a language? All those words in sigma star which are not in A. Right? So you take an arbitrary word in sigma star, determine if it is in A. If it is in A, don't include it in this language not of A, or complement of A. If it is not in A, include it. So is the idea of complement clear to you? Let me again give some examples. Okay, we did some languages before, so we'll just take one of those, you know. Okay, here is a language of all words consisting only of zeros, right? A is a language of all words consisting only of zeros. So what will complement of A look like? So let me write it in next page. How are we doing with time? Okay, we have few minutes to finish this. So my A is the language of words made over binary alphabet, consisting only of zeros. No use of one is allowed in the words of this. So I could have 0, 0, 0, 0, 0, 0, and I can go on like that. What is complement of A? That is all words in sigma star which are not in A. So it will include the word 1 in it, right? Because 1 cannot occur in it. It will also include 1, 1. But what about 1, 0?
Yes,
this will
sir,
also
it will include.
Because it's not in A. And 0, 1, that's also. So you know, all those words in sigma star which are not in A will be included in not of A, and that is called the complement of A. Different people use different notation for complement. Okay, Cosen uses this. Okay, some people use not of A for this complement of A. Some people use A bar, you know. So all these three symbols are used, but we will try to stick with Cosen's notation, although occasionally I may slip into this A bar notation. Okay, so this is just notation, some different ways of denoting complement of A. I hope the idea of complement of a language is clear to you. Okay, one last operation, catenation, and then we will finish. You know, suppose you are given two languages, A and B. A catenated, remember we given two words such as AB and BBA. We joined them to form a larger word ABBBA, right? Which is a large word. This is made out of one word AB catenated with BBA. We were catenating two words, right? We already saw this. But now what we are going to do is we are given two languages, that is collections of words, and we catenate one language is another. And how do we do this? We do this pointwise. First of all, we pick up an arbitrary element of X of A, that is some word belonging to A. We pick up some other word belonging to B, and then we catenate them. And that will give me one member of this language A dot B. Then I pick up another X and another Y, and I catenate them, and I'll get another member of AB. And I take all such possible combinations, and I will get this language A dot B. So it's a rather large language. Every element of, you know, A catenated with every element of B is included, and nothing else is included. So is the operation of catenation of language, you are getting some intuition? Let me give an example. Suppose I have got my alphabet is AB. When I don't give it, implicitly you can figure out from the, I forgot the curly brackets. So I have a language A, which is a finite language consisting of two words, A and AB. I have another language B consisting of words B and BA. So if I catenate A with B, how will I get it? First I pick up one word from A, which is A. Then I pick up one word from B and I join them. So I get the word AB. Okay. Then I pick up one word from A, which is A, and I pick up some other word from B, which is BA. And I join this two and I get the word ABA. So you see how I got two different words. Next, I choose this word from A, which is AB, and I catenate it with one word from B, which is B. So I get ABB, right? And then I pick up this word from A, catenate it with this word from B, and I get the word ABBA, right? So now I've covered all cases, so I get this four words, and that is the language A catenated with B. So not only can we catenate individual words, we can also catenate, you know, two sets of words. Okay, this is called the pointwise application of catenation to two sets. Okay, so we have got catenation of languages, and this will play a very important role in our course. So is the catenation clear to you? Let's take another example. Suppose we catenate B, B, we catenate A after B, that is B catenated with A, which is different from A catenated with B. So what do? We have to first pick up a word from B. Sorry, this should remain. This is a. So we pick up this element of B, say B, and then we pick up one element from A, and we follow this B by this element. So we get BA because we have got B catenated with A. So we first take an element of B and follow it up with an element of A, and I get this. If I choose a different same element of B, but a different element of A, AB, then I catenate them. So B followed by AB will give me BAB, right? And similarly, these other two words. So B catenated with A gives me this set, whereas A catenated with B gives me this set. This is not commutative, right? So catenation operation is another way of making larger languages out of smaller languages. So what we have done today is we have understood the notion of languages, abstractly. We have understood the notion of problem, decision problems. So decision problems are problems with yes, no answers, but they are given with abstract inputs like integers or graphs. Then we have considered the representation of these inputs as strings. And then if we collect all the yes instances of the problem, what we get is a subset of the strings. So we have defined a notion of strings and languages. And we have considered notations by which strings can be defined, as well as notations by which languages can be defined, right? That is what we have done today. And what we are going to, if I take 1 minute, we've done all these examples. When we define a language recognition problem, what we are saying is we have abstractly specified a language like this, all strings where the number of the form sequence of zeros followed by sequence of ones, where the number of zeros is same as number of ones. Given a string, which is an arbitrary string over 0, 1, we want to recognize if it belongs to this language or not, whether it's a member of this language. So the language is given mathematically as we saw today, but now we want a computational algorithm to determine whether a string belongs to the language or not. And this is called the language recognition problem, right? For which we will build a computer. So all computational decision problems are included as language recognition problems, and automata are computational devices to solve language recognition problems. So we will see this slide again tomorrow, but I just wanted to tell you about how to abstractly specify problems as language problems, language recognition problems, and all the mathematical notations required to specify languages. Languages are basically representations of problems. Okay, so that is all I have to say. Any questions? Okay, so I will stop sharing my screen and see if you have anything in the chat. TS, all these questions, all these logs of the chats that occur, they disappear, right? Or do they remain on team? Hello?
They remain on team. They remain on team.
Good. Then I'll be able to look at them afterwards. There is also a question and answer channel on Teams that I have made. You can pose your questions there and we can
Sir, I had a request. Could we have a WhatsApp group of this like course, like everyone in the course and TA maybe?
How will that help? You don't have to go via Teams. You can directly send the message.
Yeah, no, because all the other subjects are also on this thing, WhatsApp. So we have on WhatsApp, we have one group for each course that is running.
I see.
If we have one for this also, it'll be easy to keep track.
Right. It has some advantages. That is, everything about the course can directly appear on the WhatsApp. On the other hand, with 50, 60 participants, if everybody is posting messages, it could be a little bit intrusive. So I will leave the decision to the students. What I suggest is that I request the TA to start a poll on Moodle asking whether there should be a WhatsApp group or not. And if most people say yes, then we will have one. Okay?
Okay.
Let's go with the majority. Because some people could find it intrusive.
Yes, sir.
Or we can have one and then some people can opt out of it.
Yes, sir.
Okay, so may I request the TAs to form a WhatsApp group? I was not aware that most courses have them. There will be unofficial. Yes. It has no legal presence. Only thing important is what appears on Moodle and on Teams. Okay. Okay. There was a question about performing catenation on languages with different alphabets. We will take up in the Q&A channel.
Thank you, sir.
Okay, thank you. These slides will go up today and so will the video, and we'll try to put up slides ahead of the lecture too in future. Okay, so please read up these questions, and there may be a, okay, I have to discuss with TAs about a quiz on languages. Thank you.
Sir, can you start the recording?
I have to stop the recording, is it? Yes. Okay, I've done that. Thank you.